Pick up any object near you right now. A phone, a table, a wall. It doesn't matter which one. It feels solid. It feels real. It feels like matter filling space. It is not. If you took one single atom from that object and inflated its nucleus to the size of a marble, the outermost electrons would be orbiting more than 2 kilometers away. Everything between the nucleus and those electrons is empty. Not nearly empty, not mostly empty. Absolute, featureless, structureless void. And this is true for every atom inside every object you have ever touched. If you removed all the empty space from every atom in every human being on Earth, all 8 billion of us, the remaining matter would compress to the size of a single sugar cube. You are not solid. You are not matter filling space. You are an extraordinarily organized pattern of almost nothing, vibrating in a void. And the question, the one that actually matters, is why you feel like you're touching something at all. For most of human history, the question of what matter was made of had a comfortable answer. Democritus, in ancient Greece around 400 BCE, proposed that if you kept dividing any substance into smaller and smaller pieces, you would eventually arrive at a unit that could not be divided further. He called it the atomos, the uncuttable. The atom was, by definition, a hard, solid, indivisible particle of matter. This idea was intuitive, satisfying, and almost entirely wrong. For 2,000 years, it went largely unchallenged. Then, in 1897, at the Cavendish Laboratory in Cambridge, a physicist named J.J. Thomson ran a series of experiments with cathode ray tubes and discovered the electron. The atom was not indivisible after all. Something smaller was inside it. Thomson proposed a new model. The atom was a uniform sphere of positive charge with tiny electrons embedded throughout, like raisins in a pudding. It was called the plum pudding model, and it still imagined the atom as something essentially solid, dense, continuous, filled. The experiment that destroyed that picture was performed in Manchester in 1909 by Hans Geiger and Ernest Marsden, under the supervision of Ernest Rutherford. Rutherford's team fired a beam of alpha particles, positively charged helium nuclei, at an extremely thin sheet of gold foil. If Thomson's model was correct, the alpha particles should pass straight through the foil with only minor deflections. The positive charge in the plum pudding model was spread so thin that nothing should be able to bounce anything back. Most of the particles did pass straight through, but some of them deflected at large angles, and the small number, 1 in every 8,000, bounced almost directly backward. Rutherford later said this was the most incredible event of his life, as if you fired artillery shells at tissue paper and they came back and hit you. The only possible explanation was that almost all the mass of the atom was concentrated in an almost inconceivably tiny central point. Rutherford called it the nucleus. He published his nuclear model of the atom in 1911. The atom was not a dense, filled sphere. It was almost entirely empty space, with a tiny, massive core and electrons somewhere far outside it. The plum pudding model did not survive the week. To understand what Rutherford actually found, you need to feel the numbers. The nucleus of a hydrogen atom has a diameter of approximately 1 femtometer, 10 to the power of negative 15 meters. The hydrogen atom itself, measured from nucleus to the outer edge of the electron's orbital, is approximately 1 angstrom, 10 to the power of negative 10 meters. That is a factor of 100,000. Scale the nucleus up to the size of a marble, 1 centimeter across, and the atom itself would be 1 kilometer in diameter. The marble sits in the center of a sphere 1 kilometer wide, and the electrons orbit somewhere along that outer edge. Everything in between is nothing. Not air, not field, not substance. Structurally, measurably, mathematically, nothing. The nucleus contains over 99.9% of the atom's mass in roughly 100,000th of a percent of its volume. Matter is almost entirely mass compressed into a point surrounded by an enormous shell of void. The sugar cube calculation follows directly from this. The human body contains approximately 7 billion atoms. The actual matter, nuclei and electrons, occupies a vanishingly small fraction of that volume. If you removed the empty space from all human atoms, every person on Earth would compress to roughly 1 cubic centimeter, a sugar cube. 8 billion lives, every memory, every face, every city ever built, collapsed into something you could lose in your pocket. This is not a metaphor. This is the physics. But this immediately produces the most important question in this entire story. If atoms are almost entirely empty space, why can't your hand pass through a table? Why does the chair hold your weight? Why do any two objects resist each other at all? The naive answer, that solid matter blocks solid matter, is not just wrong, it is backwards. Nothing about matter is solid. The true answer is electromagnetic repulsion. Electrons carry a negative electric charge. The fundamental law of electromagnetism, established mathematically by James Clerk Maxwell in 1865, states that like charges repel each other. When your hand approaches a table, the outermost electron clouds of your hand's atoms and the outermost electron clouds of the table's atoms begin to experience mutual electromagnetic repulsion. They do not touch. They never touch. The repulsive force between the electron clouds increases as the distance decreases, until it exactly counterbalances the force pushing your hand downward. What you feel as pressure, resistance, solidity, and texture is entirely the product of electromagnetic fields interacting at the boundary between two clouds of void. The physicist Richard Feynman, who won the Nobel Prize in Physics in 1965, explained this in his famous Feynman Lectures on Physics, delivered at Caltech in 1961. He described the sensation of touching as fundamentally an electrical phenomenon. You never make contact with anything, in the sense that matter meets matter. The atoms of your fingertip and the atoms of whatever you are touching never occupy the same space. They push against each other with electromagnetic force across a gap of empty space, and your nervous system interprets this push as physical contact. Every texture you have ever felt, the smoothness of glass, the roughness of sand, the warmth of another person's hand, has been a pattern of electromagnetic resistance, not matter meeting matter. This becomes stranger still when you examine what the electrons actually are. The Bohr model, published in 1913, which you likely learned in school, depicted electrons as small particles orbiting the nucleus in fixed paths, like planets around a star. This model is wrong. In quantum mechanics, formalized through the work of Werner Heisenberg in 1927 and Erwin Schrödinger in 1926, the electron does not have a definite position. It exists instead as a probability distribution, a mathematical cloud describing where it is likely to be found if you choose to measure it. Before measurement, the electron is not at a location. It is smeared across all possible locations simultaneously, weighted by probability. Heisenberg's uncertainty principle states that the more precisely you know an electron's position, the less precisely you can know its momentum, not because of measurement limitations, but because position and momentum are not simultaneously defined at the quantum level. The electron is not a small, hard particle traveling in a circle. It is a standing wave of probability, a smear of potential location, a cloud of possibility that only resolves into a measured point when you force it to. The shapes of these probability clouds are called orbitals, and they were calculated using Schrödinger's wave equation. The simplest orbital, the 1s orbital of hydrogen, is a spherical probability cloud with no hard edge. The electron could, in principle, be found at any distance from the nucleus, though the probability drops off rapidly with distance. There is a non-zero probability that the electron of a hydrogen atom in your body is currently on the other side of the room. The probability is astronomically small, but it is not zero. More complex atoms have orbitals of extraordinary shape: dumbbell-shaped p orbitals, four-lobed d orbitals, and increasingly strange higher configurations. These are not tracks the electrons follow. They are the shapes of the electron's uncertainty, the topology of its refusal to be pinned down. Wolfgang Pauli's exclusion principle, formulated in 1925, adds another layer to this. No two electrons in the same quantum system can occupy the same quantum state simultaneously. This principle is ultimately why matter takes up space at all. When two atoms approach each other, their electron clouds cannot simply overlap and merge. The Pauli exclusion principle prevents the electrons from sharing quantum states. The clouds resist each other. This resistance, called Pauli repulsion or exchange interaction, is what gives matter its spatial extent. Without it, atoms would simply pass through each other. The chair you sit on does not support you because it is solid. It supports you because quantum mechanics forbids electrons from sharing quantum states, and that prohibition generates a force that pushes back against your weight. There is a place in the universe where this prohibition breaks down. In the core of a massive dying star, gravitational pressure becomes so extreme that it overcomes the Pauli exclusion principle entirely. The electron clouds collapse. The empty space is crushed out of existence. Protons and electrons are forced together to form neutrons, and the entire remnant star collapses into a neutron star, an object roughly 20 kilometers across that contains as much mass as the Sun. A neutron star is what matter looks like with the empty space removed. A teaspoon of neutron star material would weigh approximately 1 billion tons on Earth's surface. That is not a poetic exaggeration. It is the measured density. The sugar cube calculation for humanity was hypothetical. The neutron star is what actually happens when you collapse the empty space. The solidity of ordinary matter, then, is a kind of long-range bluff. Your hand feels solid to the table because both are playing the same game, broadcasting electromagnetic repulsion across empty space, creating the mutual illusion of contact. When you knock on wood, no atom in your knuckle ever touches an atom in the table. The sound you hear is not impact. It is the acoustic signature of two vast electromagnetic fields colliding. The pain you might feel is not damage to solid matter. It is nerve signals generated when electron clouds press close enough to trigger pain receptors. Even the sensation of your own body, the weight of your arms, the pressure of the chair beneath you, is entirely this electromagnetic theater playing out across void. Light adds a further dimension to this. When light strikes an object and bounces back to your eyes, it is not bouncing off solid matter. It is interacting with the electron clouds of the object's atoms. The color of an object is determined by which wavelengths of light the electron clouds absorb and which they reflect. The redness of a red apple is not a property of the apple's matter. It is an interaction between photons and electron probability clouds, filtered through the particular photoreceptors in your retina, interpreted by your visual cortex. There is no red in the atom. There is no color anywhere in the physics. Color, like solidity, is something your brain constructs from electromagnetic signals, a rendering of an interaction, not a property of a thing. In 1932, James Chadwick, working in Rutherford's lab at Cambridge, discovered the neutron. This completed the modern picture of atomic structure, a nucleus of protons and neutrons, orbited by shells of electrons in quantum probability clouds. But even the nucleus is not solid in the way common sense imagines. Protons and neutrons are themselves composed of quarks, bound together by the strong nuclear force, the most powerful force in nature, operating over distances smaller than the nucleus itself. Murray Gell-Mann proposed quarks in 1964, and their existence was confirmed experimentally at the Stanford Linear Accelerator Center in 1968. Quarks, as far as physicists can currently determine, have no measurable internal structure. They are point particles, objects with mass and charge but no spatial extent. The nucleus itself is mostly empty space, filled only with the force fields that bind quarks into protons and neutrons. Drill down into the densest, most solid-seeming part of the atom and you find, again, almost nothing. The standard model of particle physics, developed between the 1960s and 1970s, describes all known matter as made of point particles interacting through force-carrying particles. None of these fundamental particles have a measurable size. Matter, at its foundation, is not small lumps of something solid. It is a set of mathematical relationships between dimensionless points, generating forces that create the illusion of volume, structure, and solidity. The universe is not made of stuff. It is made of patterns of interaction in fields. Now sit with what that actually means for your life as you are living it. You are reading or hearing this with a body that is more than 99.9999% empty space by volume. The chair or floor or ground that holds you is doing so not through solidity, but through the invisible resistance of electromagnetic fields that your atoms and its atoms are broadcasting at each other across void. When you held someone's hand, your atoms and their atoms never met. The warmth you felt was photons, electromagnetic radiation, emitted by their electron clouds and absorbed by yours. The pressure of their grip was electromagnetic repulsion, interpreted by your nervous system as contact. Physical intimacy, at the level of physics, is two organized patterns of empty space exchanging electromagnetic signals. And yet, the hand was real, the warmth was real, the pressure was real. None of this knowledge makes the experience less true. It makes it stranger and more remarkable. That reality can be constructed from nothing, that patterns of void can generate warmth and pressure and color and weight, that the universe is mostly empty and yet manages, somehow, to be full. The sugar cube is not a diminishment. It is proof of something almost miraculous, that 8 billion lives, with everything they have ever experienced, can be encoded not in matter, but in the arrangement of almost nothing. You are not solid. You never were. You are a standing wave of electromagnetic relationships, a pattern written in the language of void. And the fact that you can feel anything at all, that the empty space knows it is here, is the most astonishing fact in physics.